All right, good morning, everyone. So today we will finish up our journey about all this multi-threaded stuff and finish up just talking about more general locking. And one thing you will be seeing in Lab 3 you have to implement. So first, just as a little aside, who here has programmed in like Java before? Okay, so some people have more than the other section, I guess. So there's this thing called monitors that are built into some languages. So if you have object-oriented programming, if you have mutexes, you have to remember to lock and unlock them, and sometimes that's deemed too difficult to use. So when they made object-oriented programming, they had a better idea, and they thought, let's create something called a monitor. So you can mark a method as monitored, and then the compiler will handle creating a lock for you for that individual object. And any methods that you have with that certain keyword, they will automatically have a lock at the very beginning and then unlock right before they return. So you don't ever have to remember to have any type of locking yourself, and you're guaranteed you will have mutual exclusion between all your synchronized methods because they're going to use the same lock, right? So basically, it's just one mutex per object created for you. Any method that you say is monitored has lock and unlock added for you. So in Java, if you happen to use Java, it's called the synchronized keyword, and that's the example of a monitor. So you could have a class that represents a bank account, and then you have a balance which might be, modified between different threads. So you would say that the deposit and withdrawal method are both synchronized so that you don't have any data races on your balance amount, right? So it would transform that code at the top there. The deposit would just have a lock whenever it's entered and an unlock before it returns. And same with the withdrawal, and they'll be using the same mutex pretty much. So that will make it so you don't have data races, so you don't have to argue about data races in all your synchronized methods. So that's just one shortcut that you might see, if you happen to have the unfortunate, not really a privilege of having to use Java. All right, so let's talk about condition variables, because this is, I guess, what you'll be implementing in Lab 3, and they're kind of nice to understand anyways. So they behave a little bit like Semaphores, although arguably that they're easier to understand. And they're basically like your own custom queue of threads if you know when to put them asleep and when you want to wake them back up again. So it's in the pthread library, so if you include pthreads, you can use mutexes, condition variables, threads, all that fun stuff. They have, the init method that we're used to seeing, the destroy method that we're used to seeing, and then signal, which will wake up a thread on that queue, and we'll see how this works shortly. Then broadcast, which wakes up any threads on that queue that we don't really have to worry about. Then there is wait, that takes the condition variable, and it must be paired with a mutex. And then similarly to how there's like a try wait or try lock, there's a non-blocking version called time wait that will just return after a certain timeout if it hasn't been woken up yet. But for the purposes of this, we'll just argue about wait and signal. So wait essentially adds this thread to the queue, and then signal wakes up exactly one thread that is sitting on the queue, and broadcast wakes up everything. So like I said, condition variables must be paired with a mutex, and unfortunately, the word wait is overloaded. So the condition variable wait is different than wait, which we saw before, which waits for a process to finish executing. Wait will put this thread to sleep, and when it calls wait, it must have the mutex already locked. And then signal and broadcast do not have to have the mutex locked. So why does it have to have the mutex lock? Well, you can think of it this way, that wait needs to add itself to a queue safely, so it needs to not have any data races. So if it's already holding the lock, it can just go ahead and add itself to the queue and not have to worry about data races, because it would be the only thread, right? Because it has a mutex. And then it also needs to unlock that mutex before it goes to sleep so that another thread can go ahead and do some work that might change the condition. And again, we will see an example of this. And then whenever it returns from wait, that thread essentially is going to relock that mutex before it returns from wait. So one mutex can protect multiple condition variables. Again, we'll see an example and we'll transform the producer-consumer example we saw before to use condition variables instead of semaphores. But for the purposes of this course, we don't have to worry about broadcast or time wait. We can just get away with just using wait and signal. And unfortunately, yes, these are overloaded words. It's very unfortunate because wait is also, the process wait, and signal is also the operating system sending you a signal. So unfortunately, names are reused a lot of the time, and you just have to keep track of what context they're under. So, right, the wait call doesn't contain data races, so you can think of it happening atomically if you want. And to understand what wait does, again, this is condition variable wait, not wait, which is like waiting on a process to die. So whenever a thread calls wait, this will happen atomically. So it will add itself to the queue for a condition variable. So an easier way of reasoning and thinking about this is to just assume that the condition variable just represents a queue. So it would add itself to that queue and then unlock the mutex all in one atomic operation. And then it would get blocked so that thread can't get scheduled again. And it's just going to wait for some other thread to call signal on it or wake it up. So it could call signal on it or it could call broadcast. For the purposes of this, let's just assume signal. So whenever the thread that originally called wait has something called, has another thread called signal and wakes it up, it will become unblocked so it can get scheduled again. And then the first thing it does before it returns from that wait, it's going to grab that mutex again. So that way you have a property where before the call to wait, it has the mutex locked, and then after the call to wait, it also has the mutex locked. So this is how we could transform our producer and consumer example to use a condition variable instead of a mutex. So instead of two semaphores, I'm just going to kind of have a int called n-filled, which just keeps track of the number of filled slots instead of just using semaphores to keep track of the number of empty and filled slots. I'll just keep track of the number of filled slots, and then I will create a mutex that I'm going to pair with it because I'll be modifying the number of filled slots. So I need to be sure I don't have any data races. So I'm going to do all of that while I have a mutex locked. Then I essentially could create two queues. A queue that is waiting for something that has a filled slot, and then a queue that is waiting for something to have an empty slot. And then in the producer, I would lock my mutex, and then I would have this while loop that essentially while the number of filled slots is equal to n, which is like the buffer size, so all the slots are filled. So while all the slots are filled, I should put myself to sleep, which is this wait here, and essentially add myself to a queue that is waiting for an empty slot. So there could be one, there could be many threads. That queue is just the number of threads waiting on at least one empty slot. Then, of course, I would increment, after I fill the slot, I would increment the number of filled slots because I just filled a slot. And then I could signal any threads that are waiting for a filled slot, which would be the opposite thing you'd be waiting for. And then unlock my mutex. And then in the consumer, it's pretty much the kind of dual of that. So it would grab the mutex, and then its condition is it would wait while there are 0 filled slots. So if there's nothing filled, I can't consume any data, it's all empty. So I would put myself to sleep and add myself to a queue that's waiting for at least one filled slot and with the mutex. And then I would empty a slot whenever I'm woken up, then subtract the number of filled slots because I just emptied one slot, and then I would signal any thread that is waiting on an empty slot, right? And then unlock the mutex. So does this kind of make sense-ish, that this would work and do the same thing? Okay, well, let's go to a simpler example. So let's take a look at this and see if we understand what is going on. This has an issue. So let's take a look at this code. So what is the issue with the following code? You have thread 1 that grabs a mutex, it's waiting on some condition, and then it waits, and then unlocks the mutex, and thread 2 sets the condition to true and signals on the condition. And initially assume that the condition's initially false. So let's look at this for like 30 seconds or a minute and then see if anyone can come up with some type of problem that might happen here. All right, anyone want to guess of something very bad that might happen here? Not you. So is there a situation, so if wait puts myself to sleep, is there any situation where I would put myself to sleep and I would never get signaled again? So I would never get woken up and essentially just sit there in a coma forever? Or someone brave enough to tell me what happens if even thread 1 runs to completion, then thread 2 runs to completion? Or are we all asleep? So if thread 2 runs to completion before thread 1 starts. So if we have this and thread 2 runs to completion, let's say so if initially the condition is false, right, we essentially also want at this point in thread 1, condition must be true if we reach here. So if thread 2 executes first, then it's going to flip the condition to true. And this would be thread 2. So it'd flip the condition to true and then signal on that condition, which is fine because there's no thread waiting, so it's not going to do anything. So it's essentially a no-op. And then thread 2 is done executing. Then if thread 1 starts executing, it would lock the mutex, which is fine because initially it's unlocked, right? So it would pass through the lock call and it achieved the lock. So then it would check the condition in the while loop, up here. And then the condition is true, so it wouldn't go into the while loop, it would pass. Then at the green line there, the condition is true. It could do something using that, assuming that condition is true. And then it would just unlock the mutex and then finish executing. They both finish executing. We're all good. Right? No problem with that. So the more slightly interesting, before we get into our problem, is what happens if thread 1 executes to completion first? Well, what's going to happen is it's going to lock the mutex, which is fine because it was unlocked. So it's going to grab that mutex. So now it's locked. It's the only one with it. It would check the condition. The condition is false. So it would call wait on the condition with the mutex. Dear God, that's annoying outside. And essentially add itself to the queue. So if we wrote the queue to the side for our condition variable, we would now have thread 1 sitting here in the queue, and it would be blocked. Right? Because that's part of what wait does. So it's going to add itself to the queue, also give up that mutex, and then another thread can run. In this case, there's only thread 2 that can run, right? I don't have any other choice. So if thread 2 gets scheduled, it executes. It would change the condition over to true, which is good, and then signal on the condition. And then all that's going to do is make thread 1 in the queue be unblocked now. So now it can be scheduled to run, and now doesn't have any other choice but to run. So it's unblocked now, and whenever it gets unblocked, before it can return from wait, it has to re-grab the mutex. So the mutex is currently unlocked because, as part of the process of atomically adding ourselves to the queue, it unlocked it. So it would grab the mutex again and then return from, so it would return right from wait and just start executing wherever wait left off, also with the lock still. So it would check the condition again. Now it's true, so it would fall, it wouldn't go into the while loop again. The condition would be true at the green line, and then it would just unlock the mutex, which is fine because we had it locked, right? So in that case, we executed the green line with our condition. We are all good. Right? Does this make sense to everyone? Hopefully? Okay. Now, what bad could happen? So again, here's our code. Yeah.
I have a question.
Mm-hmm.
I didn't get why we're using the mutex lock here.
So as part of calling wait, you have to have the mutex.
Oh, that is like the necessary condition for the conditional.
Yeah.
Okay.
Yeah. Yeah. When you call wait, you have to have a mutex locked. And there's kind of something going off that's related to data races, right? Our condition variable is just a variable. In one thread, we're reading from it. In another thread, we're writing. So what do we likely have in this scenario? A data race. Anyone tell me a bad interleaving of threads where the data race actually does something horrible? Wow, we're really not awake this morning. No. Yeah, come on. All right, no one? All right, well, I'll start you off. So let's say thread 1 gets executed first. It locks the mutex. That's all good. That's all well and dandy. And then as part of, the while loop, it's going to read that condition variable, right? So let's just put in a read. So it's going to read that the condition is false. So it read the condition's false, so it's going to fall into the while loop. Everyone agree with that? So what happens now if it gets context switch right before it calls wait and thread 2 executes?
So it's going to signal the condition before the waiting starts.
Yeah, so it's going to, right, if thread 2 starts executing now, it's going to change the condition equals to true, which is kind of fine. And then it's going to call signal on that condition. Well, thread 1 hasn't called wait. It's not sitting there in a queue. There's nothing in the queue, so signal just does nothing, right? There's nothing to wake up. There's nothing to unblock. It's Fine. So now at this point, thread 2 is done. We have no choice but to switch back to thread 1. And then thread 1 would call wait on that condition with the mutex. And now our condition Q would look like it would just have thread 1 in it, and it would be blocked. And now what do we can't execute thread 2, it's done. We can't execute thread 1, it's blocked. We're stuck, right? All right, everyone get that at this early hour? So that's another example of like that lost wake up we saw before, right? So you put yourself to sleep, or sorry, you add yourself to the wait queue, and the thing that should have woken you up has already happened, and you just miss that wake up, and you're essentially in a coma forever. Yeah.
Probably I couldn't get that part, but like how does T1 fix this to like restart?
So this is preemptive scheduling. So anything can happen at any point. So I'm just showing a possible preemption between the threads that cause something very bad, which for data races and showing that bad things happen, right? There's like a lot of possibilities of preemptions, but to be incorrect, you only have to show one is incorrect, and then your code is wrong. Yeah.
Does that mean the Mutex lock doesn't play any effect?
So which one?
The thread Mutex lock. Because the Mutex lock is used to prevent the databases, but why here still the databases can happen?
So in this, so the question is, well, I have a lock. Shouldn't that prevent data races? So the answer is only one thread even attempts to get the lock here, right? So if only one thread attempts to get the lock, it's just going to always get it. So it's as effective as just not having a lock, right? So like if two threads try and call lock, only one will pass. But in this scenario, I only have one thread calling lock, so it'll never pass. So how could I fix this so that it doesn't do this? Sorry? So put some locks in thread 2 and thread 1. There are locks in thread 1. How do I do that? So, someone want to save them of what I could do here to prevent this? Sure. Yeah, I need some locks in thread 2, right? There's a data race essentially on that condition variable. So if I want, I can put a lock and unlock around it, right? So let's argue what would happen in this case. So even if I have the same interleaving of threads, where thread 1 locks the mutex, now it's locked, and then reads that condition, which is still going to be false. Now, whenever it switches to thread 2 at that point, the first thing it's going to do is try and lock that mutex. But thread 1 has already locked it, right? So it can't progress. It's just going to sit there, wait. Eventually, the OS is going to have no choice. The only way to make progress is to switch back to thread 1, right? In this case, fails. Tweet 2 has lock. So then if thread 1, it switches back to thread 1, then it would call wait on that condition using that mutex. So then it would add itself to the queue, thread 1, and it would do this all atomically, so we don't have to worry about data races. and it would be blocked. And now as part of this, right, Mutex is unlocked internally as part of that wait call. So then now the only way to make progress, we can't even schedule thread 1 now because it's sitting in this condition queue. So the only choice we have to make progress is to switch back to thread 2, which was still executing that locked mutex call. But now, since thread 1 is blocked in this queue and the mutex is now free, it can go ahead, grab the mutex, and then set the condition equals to true, right? And then it would unlock the mutex. So now the mutex is unlocked, and then it would signal on that condition, which would now make thread 1 go from blocked to unblocked. Now, the only way to make progress now, thread 2 is done executing, so it has to switch back to thread 1. And then thread 1 essentially returns from that wait, so it's going to recheck the condition because it's still in the while loop. It would read the condition, which is now true. So it would fall out of the while loop, do the green line, so now the condition's true while it's executing that green line. So that's good, that's what we wanted. And then it would unlock the mutex. And then we're done. All right, any questions about how that works? Yeah.
When thread 1 waits and the mutex is unlocked, it's like, what happens automatically, or what happens there?
Yeah, so as part of the wait call, what atomically is going to happen is it's going to add itself to the queue and unlock the mutex, right? All the steps here. So it's going to add itself to the queue for the condition variable, unlock the mutex, and then be blocked so it can't be scheduled again. And then whenever some thread calls signal, in this case, there's only one thread sitting there, so it's going to wake up that thread. It would get unblocked, so it can be scheduled now. And then before it returns from the wait, it will grab that mutex again, so the mutex is locked when wait returns. Okay. So if we have that with lock and unlock, one question might be, well, do I really need that while loop? Because, if some thread signaled me, it's because the condition's now true, and what the heck? Like, I know it's true, why am I in a while loop just to check that it's true again? Well, basically, if your code looks like this, where you have an if condition, more likely than not, there'll be several threads swapping the value of that condition. So thread 2 could set it to true and then signal that, hey, that condition's now true, you should wake up if you're waiting on it. But likely, something like thread 3 would also set the condition to false, or just some other thread in your program would likely set it to false. So you could be in the scenario where thread 1 executes, so thread 1 could execute, grab the mutex, be locked, check the condition, which is false, wait, so it would add itself to the queue, unlock the mutex, and it can't be scheduled to run again. And then thread 2 could come in, grab the mutex because now it's unlocked, set the condition to true, unlock the mutex, and then signal that thread 1 to wake up, which is going to try and grab the lock. But thread 3 could have already been waiting for that lock before the signal. So thread 3 would grab the lock first ahead of thread 1, set the condition back to false, and then unlock. And then whenever you return from wait here, you would see that condition as false. So if you just had an if and it just dropped out, at this line could execute while the condition is equal to false, which is exactly what you don't want, right? And also, fun fact that this wait call, at least by the spec on some operating systems can return even if the condition does not change. So it can just wake itself up just because it wants to make your life difficult. So just in all circumstances, you should always just do a while loop just to double check that the condition's actually true before you start executing anything, right? Cool. So no questions about that. Hopefully that woke people up a little bit. All right, so condition variables kind of serve the same purpose as semaphores. You can kind of think of semaphores as a special case of condition variables. So you could just create your own integer with a value, and then, you know, whenever you do something, you can increment it, and then you don't have to do a signal. And then if you do, and then to implement your weight, you would just decrement it, but you first check if the condition, if it's equal to 0, you would just weight yourself, right? And then that way it behaves exactly the same as a semaphore. So condition variables are kind of just a more general solution to semaphores, and it's generally a bit easier to read if your conditions are very, very complex. But, you know, implementing a semaphore as a condition variable is easy, but you can actually do the reverse. There's papers on that. It just gets kind of messy, and you would never want to read and debug something like that. So you generally, the two tools do the same thing, but the only difference is depending on what you're doing, one is much easier to read than the other one. So you will kind of get a feel for that as you go, you know, as you practice this stuff. So the next thing we can talk about is locking granularity, and that's the extent of your locks. So between, considering if you have a mutex, you know, all the code between lock and unlock is going to be essentially running in serial. So you want to keep that as small as possible, while also still preventing data races, because that's your #1 goal. You need to prevent data races, or else your program's going to behave incorrectly. Although there are some cases where data races might be okay, but you really have to argue about that. But if you lock large sections of your program, that might be bad. You might want to divide the locks into smaller sections. For example, what if you want to parallelize your hash table in lab 1? So who can do that now? Because you should be able to. So did anyone use like linear probing for collisions? Good, because if you use that, you're probably screwed. So if you just had, you know, if every slot of your hash table was just a list, you could have a mutex for each individual slot. And then that way, you know, you don't have any data races because you protect a slot. You know that any collisions will resolve to the same slot. So if you just run everything in the same slot in serial, then you won't have any data races. You will be fine. And then likely, if your hash function distributes things well, it can essentially fully parallelize itself because, right, the odds of hitting the same slot are pretty low. So you could actually pretty easily parallelize it. Well, if you have linear probing, where you know if there's a collision, you go to the next slot and on and on and on again, you won't know how much of your hash table to lock, and you're essentially, the safest thing to do is to just make the whole thing run in serial. So now you're getting into the situation where how you implement your algorithms dictate how easy it is to parallelize it, which is going to be a major consideration, especially in today's day and age when you have multiple processors. So some things to consider about locks too is the overhead of the locks, because they're not free. You have to create them. There's going to be some cost to locking and unlocking them. And then even more majorly, there's a scenario of deadlocks that we'll look at. So overheads associated with locking, and overhead is just any time you are wasting CPU on operations that don't contribute to actually running your application. So for example, for locks, there's going to be some memory overhead. So if you create, you know, 1 billion locks, you can't create 1 billion locks for free. They have to be stored in memory somewhere. If you have 1 billion of them, even if they only take up a few bytes, they're still going to waste a lot of space. There's costs, right, to initialize them and destroy them. There's also time required to do the lock and unlock calls. And depending on what, how big your critical section is, the time to even unlock and lock it might dominate your critical section. So in which case the cost of that would be significant and you might need to rethink what you're doing, right? And the more locks you have, the worse it's going to get because this is times the number of locks you have, right? So we haven't talked about deadlocks yet, so here we get to talk about deadlocks and the conditions for deadlocking. So the more locks you have, the more you have to worry about this. So there are 4 conditions you need to have for a deadlock. One is mutual exclusion, which if you have mutexes, of course is going to happen because they're for mutual exclusion. 2, you have to have something called hold and wait. So you have a lock and try to acquire another. So you already hold a lock and you're trying to get another one. So you need at least 2 locks to deadlock. You also have to have no preemption, which means you can't take simple locks away. That doesn't mean you can't have, you can't context switch between threads still. The preemption is preemptible locks, so I can take a lock away. So like I can just make it unlocked if I want to. So to have a deadlock, you can't have this. And for simple mutexes, if you have the lock, nothing can take it away from you, unless it's yourself. And then 4, you have to have a circular wait. So you're waiting for a lock held by another process or thread. So this is the simplest deadlock example that I can think of. So consider 2 processors or 2 threads, each getting 2 locks. So the code in thread 1, it tries to get lock 1 and then get lock 2. And then in thread 2, it tries to get lock 2 and then lock 1. Well, since we're in the land of threading now, we have to argue about any preemptions between 2 threads resulting in bad behavior. So one bad preemption we could get is thread 1 runs get lock 1, it locks lock 1, and then we get preempted to thread 2. Thread 2 locks lock 2 and now has lock 2. Then at that point, if it tries to get lock 1, it can't because thread 1 has it. And then if we context switch back over to thread 1, it will try and get lock 2, which it can't do because thread 2 has it. So we're at an impasse here, right? Each thread is trying to get the lock that the other one has while it's still holding another lock, and neither can make progress. So does that make sense why that's a really bad thing that can happen? So neither thread can execute at this point. We're deadlocked. Our program can't make any progress anymore. So to prevent deadlocks, one of the simplest solutions is to just ensure some type of ordering between locks. So if both threads always got lock 1, then lock 2, then you won't have any issues, right? So you can only get lock 2 if you already have lock 1. So it's kind of implied that if you can get lock 2, you already have lock 1. So if 2 threads race, it's whoever happens to get lock 1 will also get lock 2 because you can only get lock 2 while you have lock 1, right? So if it's the same example where we have 2 threads, one's trying to get lock 1 and then lock 2, whoever gets lock 1 first is going to also get lock 2, right? So we won't have any deadlocks. So does that make sense? Okay, cool. So you have to be real careful about this too, because generally you pass things by pointers. So if you have some code that looks like this, it doesn't necessarily that means lock 1 actually points to the same thing every time. So fun questions to ask is like, pass this by pointers and then you actually switch the arguments around so that it actually looks like something like that. And then that would deadlock, right? So even though the code looks like it acquires them in the same order because of pointers and all that stuff, it might not. So that's fun. The other easy way, if you don't want to ensure ordering between threads, is to use a try lock. Because remember, one of the conditions is hold and wait. So this is eliminating that condition necessary for deadlocking. So now this is finally where try lock comes into place. So instead, if you can't ensure order between the lock, you can do something like this. So you can lock 1, and then you can do a try lock on lock 2. And what try lock will do is it will try and grab the lock and then tell you if it has it locked or if it has it unlocked. So in the case where it's not equal to 0, it means that it did not successfully grab the lock. So if it did not successfully grab lock 2, it would unlock lock 1, then wait, put itself to sleep, yield, do something here, then hopefully the thread that is waiting on lock 1 would be able to grab it now because we unlocked it. So we freed it up. We're not holding and waiting on it. So at this wait call right here, we have neither lock. And then next time we go through the loop, we try and lock the thread again and then see if we get lock 2. Again, if we don't, we'll do the same thing. If we do get the lock, we'll fall out of the while loop and then be able to run our protected code here while we have both locks. And then, of course, we would unlock both lock. So this won't deadlock because we eliminated hold and wait. So if we can't get lock 2 while we have lock 1, we will just give up lock 1 and essentially yield, hopefully have another process that was using lock 2. It will be able to unlock it or do whatever it needs to do. Right, so any questions on this? Makes sense? Cool, all right. Let's go look at our code too. So here's the producer consumer implemented in terms of condition variables. So I'll create a mutex for the condition variable, and my condition is essentially the number of filled slots, and then have 2 queues, one for has empty and one for has filled. So I would just initialize them, and then initially the number of filled slots is 0. So now my producer code, it would lock the mutex, check the number of filled slots. If it's equal to the buffer size, it needs to wait on an empty slot. So again, it would add itself to the queue using that mutex, and then eventually, whenever it breaks out of this while loop, it will be active and the number of filled slots will not be equal to the buffer size, so there'll be at least one empty slot. So then in that case, I can fill the slot, increase the number of filled slots, and then I would signal any threads that are waiting for a filled slot and then unlock the mutex. Right? And then same thing with the consumer, where I would lock the mutex. The condition here is if the number of filled slots are 0, then they're all empty. So I shouldn't empty anything because there's no data to get. So I would put myself into the has filled queue where I'm waiting for a filled slot, then empty a slot, decrease the number of filled slots, and then signal anything waiting for an empty slot, and then I would unlock it. All right? That makes sense to everyone? So for this, we had 2 options, essentially. We could use a Semaphore, or we could use our condition variable. So here's our Semaphore implementation again. So between the 2, who thinks the Semaphore one is clearer? No one? All right, then who thinks the condition variable one is clearer? One person, sweet. So they're equivalent. I guess for this, I would argue that the condition variable one is a bit clearer because you actually know the conditions. So the number of filled slots and then is what you're waiting on. You actually want to check if they're all empty or they're all full. And then you don't have to argue about the initial value of the Semaphore because that actually determined correctness. But I guess we're not terribly awake now, so we can just go ahead and think about this for later. So I guess I can just, yeah, I guess we can just end early and go take a nap, I guess. So we explored some more advanced locking today. We have another tool to ensure order. Condition variables are generally clear for more complex condition signaling. You have to implement them in lab 3, I believe, so that'll be fun. And that woke someone up at least. When you are trying to use locks to speed up your program, right? You're trying to parallelize things as much as you can. The locking granularity matters to how much you can parallelize your program. So you want to make it as small as possible. But now, in addition to preventing data races, which you should do, you now have to prevent deadlocks. Otherwise, right, if your application deadlocks, it's not going to make progress. So let's remember, I'm pulling for you. We're all in this together.